Once again, I welcome you to another series of this class. We'll continue from the previous slides that we were looking at when we were looking at the geometry of the molecules. Now, in this, we'll continue looking at examples, and the examples that we'll look at is phosphorus fluoride. Now, first we'll try to draw the structure of phosphorus fluoride. Then after which we try to determine what the shape could look like. So now what you get, of course, phosphorus 5 fluoride, meaning phosphorus will be in the center, and phosphorus is in group 5, so the valence electrons will be 5. So you have phosphorus with 5 valence electrons. Now, this will react with 5 fluorides, so you get a fluoride, a fluoride, a fluoride, a fluoride, and a fluoride. Like chlorine, each fluoride has 7 valence electrons. So what you get is that each one of them will have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, one of the things that you notice is that fluoride does not obey the octet rule, in the sense that it has d orbitals that are able to expand its octet. So it has d orbitals which allows it to expand its octet. So now, to determine the shape of the molecule, remember the shape of the molecule is determined by the bond pairs. So we'll count the bond pairs. So there's 1. So we'll use this stuff. There's 1, 2, 3, 4, 5. So when it comes to the bond pairs, we have 5. Lone pairs, we have 0. Now, what would be the stable structure that will result to 5 bond pairs? Now, what will happen is that phosphorus will form 2 shapes combined together. So you have a trigonal bipyramid and a linear. So you get a trigonal bipyramid like this and a linear. So in this case, it has 2 bond angles. So between this is 120 and between that is 90 degrees as a bond angle. And this is normally called as a trigonal bipyramidal. So bond angle is 120 and 90 degrees. Because you have this trigonal planar is like this, it's 90 degrees from this linear. So it's more or less, when you're looking at it in the angle, it will look like this. So this is a trigonal. So in most cases, it will look like that. So a trigonal bipyramidal with 120 and 90 degrees bond angle. Still looking at more examples, we can look at sulfur 6 fluoride. Same applies. Sulfur has d orbitals, so it can expand its octet. So meaning it does not obey the octet rule, it can expand. So if you look at sulfur, sulfur is in group 6. So you have 1, 2, 3, 4, 5, 6. Then it is bonded to 6 fluoride. So you get 1 there, 2, 3, 4, 5, 6. So each one of them will have 7, 1, 2, 3, 4, 5, 6, 7. So it's fluoride 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So you have fluoride, then 1, 2, 3, 4, 5, 6, 7. Fluoride. Then the next thing that you do is to count the lone pairs. So in counting the lone pairs, you have 1, 2, 3, 4, 5, 6. So in lone pairs, there are 6 lone pairs. So now what we have is that bond pairs will be equals to 6. Lone pairs is equals to 0. So now what will be the shape of the molecule? The shape of the molecule will be an octahedral with bond angle 90 degrees. This is how an octahedral looks like. So you have a square like this. It's a bit different from a trigonal bipyramid because in where there's a square, there's a trigonal. Then there's also now it forms a pyramid, meaning one bond is going up, another one is going down like that. So same applies here. 4 chlorine will be in the same plane. Then one fluoride will be going up and one fluoride will be going down. So 4 fluoride, same plane, one going up and one coming down to give you what you normally refer to as an octahedral. And the bond angle in the octahedral is 90 degrees. So basically, this is how an octahedral looks like. An octahedral will look like this. Now, what we're discussing the shape of the molecule with regards to only lone pairs. What happens if we bring in the, sorry, we're discussing with regards to bond pairs, right? So meaning equally repelled or equal repulsion. What happens if we bring in lone pairs? What will happen? So when you bring in lone pairs, it will give you an irregular shape. The reason being the repulsion between lone pair are more than bond pair. So this will be number 1 in terms of repulsion, followed by this, then this will be the least. So in short, what the lone pair does is that it squeezes the molecule a bit. It distorts the structure of the molecule, and this is what you normally refer to as the irregular shapes. The repulsions are not equal, so you get extra repulsion from lone pairs. Let's look at examples. We start with ammonium, right? Ammonium, the central atom is nitrogen. Nitrogen has 7 electrons. It has 5 electrons. So it's 1, 2, 3, 4, 5. Then it's bonded to 3 hydrogen. So you have 1, 2, 3. So you have hydrogen, hydrogen, hydrogen. So you get this, you get that. So now if you're looking at the pairs, there are 2 types of pairs. So there's 1, 2, 3 as lone pairs, and 1, 2, 3 as bond pairs, and 1 as a lone pair. Let me try to draw that again. So you have nitrogen, 1, hydrogen, hydrogen. So you have 1, 2, 3 as bond pairs. So bond pairs that equals to 3. Then we have one lone pair, so the lone pair is 1. So what do we expect from here? We'll have an irregular shape. From the previous example of methane, 4 gives you a tetrahedral with 109 bond angle. Now, in the previous slide, we discovered that the repulsions between the lone pair are more than between the bond pair, lone pair, and the bond pair, bond pair. So what does that do? That will now squeeze the molecule a bit to reduce the bond angle. So this is what you get. It will be what you normally refer to as a distorted tetrahedral. So it will have 1, 1, 1, 2, 3, 4. So it's a tetrahedral, but it's distorted because the repulsion that we experience between this lone pair and this are more than the repulsion between those and those. What happens is that now this bond here is squeezed a bit. So it will reduce from 109.5 to 107 as your bond angle. Then the shape will be more or less like a pyramidal. So that's what you expect to see. You expect a shape that looks like more or less like a pyramidal. So what you get is that when you're drawing the shape of ammonium, you have nitrogen, then 2 lone pairs, then you have hydrogen, hydrogen, and hydrogen. So it will look like this, and the bond angle 107, like that. So this is how it looks like. It will look more or less like a pyramidal, but in short, it's just normally called as a distorted tetrahedral with a bond angle 107 in terms of instead of 109 because of the lone pairs. Let's go to water. All right, H2O, hydrogen oxide, and the common name is water. So the central atom, of course, is oxygen. Oxygen has 6 valence electrons. So you have 1, 2, 3, 4, 5, 6. Then it's bonded to 2 hydrogens. Water is bonded to 2 hydrogens. So you have 1 hydrogen here with 1 electron, 1 hydrogen there with the 1 electrons. So now what you get is that when you begin to count the pairs that are there, the bond pairs will be equals to 2. Lone pairs will be equals to 2. So you have bond pair 1, 2, lone pairs 1, 2. Now what does this do, or what does this entail? It reduces the bond angle of a tetrahedral further. So now what you get is that the bond angle of a tetrahedral will be further squeezed. So water will look like this. So there will be repulsion between a lone pair. So water will have a lone pair, bond pair, lone pair, lone pair repulsion, and lone pair, bond pair repulsion. So you see there will be this repulsion between the lone pairs and this repulsion between the bond pair and the lone pair. So what are the consequences? That the bond angle reduces from 109.5 to 104.5. So if a question is asked to explain why water has a bond angle of 104, what you say is that water has 2 lone pairs that further squeezes the bond angle from an ideal tetrahedral, which is 109.5 to a distorted one, which is 104. So which is 104.5. And the shape mostly it's angular. It will still be a distorted tetrahedral. The reason being lone pair repulsions are more in water. Still looking at more examples, let's look at xenon tetrafluoride. Now, xenon is the central atom and it has 8 electrons. So you have 1, 2, 3, 4, 5, 6, 7, 8, bonded to 4 fluoride. So you have this, so this is a fluoride, 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 fluoride. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So in terms of the pairs, we can count. So you have 1, 2, 3, 4. So you have bond pairs, there will be 4. Lone pairs of 1, 2. So lone pairs, there will be 2. So that gives you a total of pairs, which is 6. Then from what we saw, 6 is an octahedron. Now, what does it mean? 6 is octahedron. But what do we get? The geometry that we get from here is a square planar. So you have this and the lone pair going up and one coming down, giving you a square plane or an octahedron. So the 6 is based on the octahedron, but the shape that you get is different. Let's go to those that have multiple bonds. Now remember, we said if a double bond and a single bond and triple bond are treated in a similar way. Let's look at carbon dioxide. Carbon dioxide is something that looks like this, and basically if you count the lone pairs, so if we use this as a structure, so you have, since double bond and single bond are treated the same way, so when counting the lone pairs we count them in a similar way, so meaning this would be 1, 2. It doesn't matter whether there are 2 double bond. Okay, let's start this again. In drawing the structure, you have carbon in the center. So you have 1, 2, 1, 2. Then oxygen. So you have 1, 2, 3, 4, 5, 6. So another oxygen. 1, 2, 3, 4, 5, 6. So looking at the pairs, you count this 1, 2, 3, 4. But remember, when we are looking at the pairs between two atoms, no matter how many they are counted as a unit. So in counting the lone pairs, these 4 will be 1 and these 4 will be 1. So in terms of lone pairs, in terms of bond pairs, this molecule has the bond pairs will be equals to 2. Doesn't matter that if there are 4 here. As long as these 4 are bonded just between 2 atoms, then they are counted as 1. Remember, a single, double, and a triple are treated in a similar way. So in short, what will be the linear of the molecule? Then the lone pairs will be 0. So the molecule basically equals to be linear with 180 degrees bond angle, like in beryllium chloride in the previous slides. So this is what you expect to have. So now looking at other examples, you have this. The lone pairs is only 1, so the bond pairs is 1, 2, 3, 4. So it will be a tetrahedral with 109 bond angle. If you look at this as 1, 2, 3 bond pairs and 1, 2 lone pairs. So this will have more or less like a T shape with 90 degrees bond angle. Same applies, you have this molecule, it has 1, 2, 3, 4, 5 bond pairs and 1 lone pairs. So it will be more or less shaped like an umbrella with 90 degrees bond angle. So there's some questions for your own practice. You can do them at your own free time, and I'm sure that most of them will be addressed or will be answered in the tutorial. Okay, so solutions have been given. So just try to see if you can solve these questions by yourself. Then after which you can compare with the answers and see whether what you're solving is basically correct. Okay, so you have a table that you have to memorize in view of the shapes of the molecule that you have. For example, you have two ligands, non pair, so it will be linear. 4, it will be tetrahedral. 5, to be trigonal by pyramid. Then 6, ideally to be an octahedral if they are not lone pairs. So what you get for 2 linear, 3 if they are no lone pairs, it's a trigonal by pyramid. If there are 2 lone pairs and 2 bond pairs and 1 lone pair, it's more or less like a bent. Then if you have 4, 3 lone pairs and 1, it will be tetrahedral or trigonal by pyramid. So now this is using the group electron geometry, and this is using the molecular shape of the molecule. Then it gives you the bond angle. So you can look at this table at your own free time and see how different shapes basically are elucidated or they are determined. So basically what you need to know is that you need to understand if we give you the structure of the molecule or we give you the chemical formula of the molecule, are you able to predict what the geometry will be based on the repulsion theory or the valence electron or valence electron repulsion theory? I think on this I'll end here and I'll continue in the next slide, and I hope to see you soon. Thank you very much.